Alright, yeah, physics video. Yeah, I thought I'd better explain, just as I had a private conversation and I realized that, you know, which sometimes you see something because you see it, you can recognize it, and it's like really obvious. And then somebody's not seeing it because that little element that you're so obvious to you, the mechanics, they're not seeing until so you really have to give them that, they have to see what you're seeing for them to say, oh, okay, now I understand it. So this idea, like, finally makes this argument that there would be a problem with some sort of photonic pressure having something to do with the angular momentum of bodies. And that as they move, they would build up more pressure in front of them and less pressure behind them, and therefore this couldn't work, that kind of thing. And it's sort of based on the idea, I mean, it makes sense in the sense that you understand the light's coming in as particles, and so obviously if some other particle's moving faster, technically, towards something, it's going to interact with more of these little things in a given amount of time, and that creates some sort of energy differential. And likewise, as it's moving forward, it's running away from things trying to get to it, so the pressure behind it would be less. So it's kind of mechanically obvious. And then even my example of a school of fish, has the limitation where fish can move in two ways at once. A fish can be going sideways at 30 miles an hour, but it can also be moving this way, because of current or some other mechanism. So that's sort of the flaw here, is that I have to emphasize this point that light can only move in one direction. It only has momentum in one direction. It can't be moving two directions at once. So that's where people aren't getting it. So maybe. So I just thought I'd go over it and try to explain that idea, that what you have to understand is, so here's, just think of the matter as having only two directions. Okay, let's just say it goes this way or it can go this way. And so, as pointed out, if something is coming at it straight, it's purely kinetic. That is, it's like two pool balls in a vacuum. One hits the other. This one just goes right through the other one. Nothing happens. Everything remains exactly the same, in the sense that the energy is just transferred between the two, and there's absolutely nothing that happens. Nothing happens, essentially. So you obviously can't change. There's zero angular momentum as they hit each other, so there's zero chance of changing anything. There's just nothing that can be changed. So when something starts moving, a school, a fish, it means more fish are doing that. So you kind of X off the fish that are doing that. And then there's fish that are swimming away from you. And so you obviously can't get them because they're going away from you, let's say. Okay, so there's one of those. And the exact opposite ratio would exist at the back end, right? There would be more fish running away from you that you can't hit, and there'd be that one fish that's coming at you that you can't hit. So all you have is the stuff going sideways. It's the only stuff you can react to. So the thing to understand, though, is that the stuff going sideways, so let's say these are the last bits of matter that can be seen, okay, because they're going sideways. So it's like the school of fish in the sense you see the little flashes that go sideways, and those, the rest of the school becomes invisible except for the flashes of the fish going sideways. So, but understand that anything that doesn't have an angular momentum going straight at you or away from you is going to be relative to these fish, relative to these are going to be going that way. Okay, so relative to the front, relative to the momentum of the entire body, anything going sideways is going that way. It's going backwards. Okay, it's relative to the ones moving forward. Correct? So you can sort of understand that, right? That if something's going sideways, it doesn't still have forward momentum. It's light. It can only go one way at the speed of light. It can't go two ways at the speed of light. So as things start moving this way, it's still only going this way. It's not going this way. So it's going to lose, it's going to have to fall backwards, in other words, relative to the front. So if there's a fish going sideways in the school of fish, he decides to go sideways, and the school is predominantly going 30 miles an hour that way, right, towards me, then as it goes sideways, it's going to start moving this way relative to those fish. It's going to lose ground. It's going to start ending up at the other end of the school. And so the argument I would make is that's how you have to understand it, that the pressure from the back still exists because the stuff going sideways is moving, relatively speaking, it relative to the front towards it. It's not really moving towards it, it's just staying still like it always did, because it's moving the speed of light. And likewise, from the stuff coming from the front, it's obviously not coming at it at the speed of, at an increased speed. So it's not encountering more photons because it's declining relative to the other fish. And so all you're talking about is the time, the amount of time in this given quotient that fish go this way. And as something gains acceleration in a direction, the amount of time fish are going sideways starts declining, because obviously they have to go this way pretty quickly or they'll fall right out of the school, right? They'll just completely fall out of the school. So the little flashes become quicker and quicker and quicker and quicker, which means there's less and less to be interacting with, but still the differential between the two sides will remain the same, because anytime it's moving sideways, it has no momentum in either one of the forward or the backward directions. So when it's moving perfectly sideways, it has no momentum forward or backward. So it's obviously not moving faster relative to the forces coming in. It's not encountering more or less photons from the external world, because from its perspective, it's not moving relative to those. And obviously, as the angle changes, the percentage of that speed differential changes. But as soon as you change the pitch, you're going to change percentage-wise how much it's declining, how quickly it's declining. Yeah, and there are, obviously there's still photons in a system. Like if it's doing a figure 8, there's still photons going exactly the opposite direction of the fish at the lead going this way. So technically, if they're going the speed of light, this would be 300 and 400 and 360,000 miles a second difference in where they're going to end up time-wise. So obviously they can't spend too much time going this way, or they'll end up out of town. But again, it's the nuclear physics. It's not, so these time scales have to be, you have to understand that this is in their world, they're only doing these stuff for tiny, tiny, tiny fractions of a moment of time. Gee, I hope that helps. Probably still doesn't. Just understand that declining thing. As soon as you're not going forward, okay. As soon as you're not going forward, you're going backward relative to the lead fish. So you're not encountering more rain. So when Feynman says if you run into the rain, well, that's fine, but that's not what your photons are doing. The photons inside your body going sideways are not running into the rain. They're not moving forward. They're going backward. I know that's hard to think of in those terms, right? Because you're saying, well, then why doesn't it just fly out of the back of your head and it's gone? Because it's the amount of time it can spend doing that. It doesn't spend as much time doing that relative to the time spent doing the other things. So that's why it doesn't end up declining out of the back of your head, is that it gets with the program and goes forward again until some time where something has to go sideways again. It goes back, and then it goes forward again, and then it goes back, and then it goes forward again, and then it goes back. So you have to understand that it goes to the end of the line, gets back in the speed lane, goes back to the front, and then goes to the end of the line, swooshes back to the end of the line again, and then goes back to the front. I mean, you have to understand that it's still doing this circular thing, and that's what Feynman's missing from his argument, is an understanding that it's that the mass is made up of movements, and that those movements, some of them, are not. They're not all going in this. They can't acquire the momentum of the thing they're leaving. Just like if you're shine a flashlight, if you're moving in a train and you shoot the flashlight out the train window, or you throw something out the train window in a perfect world, in a perfect vacuum or whatever, yeah, it's going to disappear because it's not going to stay with you. It's not going to keep your momentum. It's going its way, and it has no momentum from your perspective. It's just going to disappear. Yeah, so I'm sorry if I've been a little arrogant about this, because now I'm thinking about it and I'm saying, okay, now I understand why people aren't understanding. It's because, yeah, when you try to explain it, you're saying, okay, wait, okay, they can understand the kinetic thing, like if something's coming right at it, it goes right through it, so that they probably get. But yeah, it does seem a little, I mean, now that I'm thinking about it, it is awkward to think about the fact that the matter's not moving the same, all the stuff inside of the school isn't moving the same speed, and that if all the fish were coming at me and one tried to go sideways, that it would very quickly end up at the back of the school. Yeah. Okay. Yeah, that's understandable. So there's probably a way I have to phrase that, is that light can't have momentum in more than one direction. Light only has momentum in one direction. So as soon as it has an angle relative to you, okay, then it can't be moving like that. That it's not doing. It's moving like this. It's not moving like this. Yeah. It's not doing both. Okay. Enough said. Hopefully. Yeah, I have to find a better way to draw. I guess the real thing is people have to understand the geometry of it. It's like we're back to the idea that you have to understand a Planck constant, and the fact is that if something's moving a shape through these squares, and that shape starts moving in a direction, that it still has to do all these squares, and it's doing these extra squares forward each time, and so it's going to get slower and slower to draw this figure 8. I don't even know if that quite does it. Well, anyway, I'll try again in the future, but I think I said enough here to help you understand. That's why Feynman's analogy doesn't work, is because the matter that is going to have its angular momentum changed, the matter that's left to be changed, is going to be spending less time in that condition exposed to the rain, from his perspective. Okay, till next time. And obviously as the stuff moves backwards, the rain in the behind, the low pressure rain, is going to have more opportunity because it's spending more time moving away, which is towards the back end pressure. The pressure ends up equalized. The end result is you can't unequalize the pressure. Okay. That's probably not the best way to say it either. I mean, it's the truth, but I guess I have to come up with an equation that has a 0 in it. And it all equals 0 in the end. There's no change in angular momentum. But anyway, okay. Till next time. I mean, no change for a body that already has plain velocity and isn't accelerating. Yeah, okay, till next time.